electric field at the fourth quarter? Is that what it was? So find the electric field here. And we were given some distances, 3 and 4 meters. So this is 3 meters, 4 meters, therefore, this is 5 meters. And therefore, this is 37 degrees, right? Okay, so what is the electric field generated at the fourth corner by Q1? Is it pointing towards it or away from it?
Away.
Away. So that would be this way. What's the magnitude of that? So that'll be 9 times 10 to the 9th. Q1 is 2 microcoulombs. And the distance is 5, and we need to square that, right? So that would be the 10 to the 9th and the 10 to the minus 3 is 1,000. So that's 9 times 2 is 18,000 divided by 25. And I don't know what that is, but you know, some number.
720.
720?
Yeah.
Okay. Thank you. So 720 newtons per coulombs. Now, what about this point charge over here? It generates an electric field here pointing which way? Towards it, right? So is that 3 or Q2 or Q3? Q3? So I'm going to call this E3. And what's the magnitude of that? It's K Q3 divided by R squared. So that would be 9 times 10 to the 9th. That charge is 3 times 10 to the minus 6 divided by 3 squared. Well, 3 squared is going to cancel this, right? So that makes this 3,000. And then this charge here generates an electric field over here pointing which way? Towards it, right? So is that E2? So what is E2? It would be K Q2 divided by R squared. So that would be 9 times 10 to the 9th. This is 6 times 10 to the minus 6. And this distance is 4 meters. So that would be 4 squared. So that would be 9 times 6 is 54. And then it's 1,000 because of the 10 to the 9 and 10 to the minus 6 divided by 16. And I don't know what this is. But what is that?
3375.
3375?
Yeah.
All right. So what we need to do is we need to add those 3 vectors. So we can therefore write, E net will be E1 plus E2 plus E3. E1 is this one, right? So this angle here is 37 degrees, right? So that would be, it has the next component to the right, so that would be E1 cosine of 37 degrees I hat plus E1 sine of 37 degrees J hat. So that's E1 plus E2 is what? E2 is this one, right? The magnitude is 3375 newtons per coulombs. That's to the left. So that's minus I hat. So this would be minus 3375 I hat. And E3 is in the negative y direction. So that's minus 3000 J hat. So this is E1 is 720. Cosine of 37 degrees is 4/5. This is 720. Sine of 37 degrees is 3/5. Minus 3375. I hat minus 3000 J hat. So, my goodness.
It's 576.
This is 576?
Yeah.
And then minus that is gonna give me what? Minus 3375 is what?
432. Oh, sorry.
27.99.
27.99. Agree, people?
Yeah.
And then we're also gonna have a negative, right? So 3,000 minus whatever that is. 25, 50,
2568.
58. Thank you.
68.
2568.
Yeah.
All right, so this is the electric field net, but this is not what I asked. Yes, I did ask for the resultant electric field, but the magnitude of it and the direction of it, right? So this electric field has an x component that points to the left, that's 2799, and a y component that points downwards, 2568. So the net electric field is this in magnitude, and we can specify that direction. So the magnitude of the net electric field is, well, Pythagoras theorem, right? 2799 squared plus 2568 squared, square root. And for the angle, this is 2568. If I take the tangent of theta, it's the opposite side, right? 2568 over 2799. Take the arctangent, and that's so many degrees. And then E net is, I don't know what that is, in newtons per coulombs. And this one is going to be as shown here. So what angle do you get and what magnitude do you get?
42.5 for the angle.
The angle is 42.5.
That's what I got.
That's what I got.
And the magnitude?
32.799 squared plus 2.
3.80 times 10 to the third.
I got
3,000 and what did you say?
I got 3,798.
Yeah. 3798.
Yeah, 3 plus that.
I just did 360 at the end.
It's okay. That's it? How long did that take? A little bit, right?
6 minutes.
So you find this is a positive charge, it generates an electric field there that points away from it. This is a negative charge that generates an electric field that at that point pointing towards it. This is another negative charge that generates an electric field pointing towards it. We find the magnitudes of these electric field vectors, k cubed r squared. And then it's just a chapter 1 problem. Add 3 vectors. What's the magnitude and direction of those, of the sum of those 3 vectors? So this vector here points in the negative y direction. That's this one, and that's this one. And this vector here points in the negative x direction. So that's this one, and that's this one. And E1, the electric field generated at this corner by the charge at the opposite corner, has both an x component and a y component. And that's this, which is this. And the rest is just algebra. Questions? It's yet another exercise in adding vectors, except that the physics you need to know is how do you calculate the magnitudes and directions of these 3 electric field vectors. If you remember that the positive charge generates an electric field pointing away from it, and a negative charge generates an electric field pointing towards it, then you have the correct directions. And then the next step is to get the magnitudes. That's just k cubed r squared. And then the rest is just adding vectors. Okay. Questions? No? Okay. chapter 22 on Gauss's law.
Yes.
Can I erase this?
Yeah.
I think we were working with cylinders, correct?
Yeah.
And we did some metallic cylinders, hollow with a hole inside and a wire, I think, on the axis, correct? And I gave some charge spring length, and in just a couple of seconds you were able to figure out how much charge would be on the inner surface of that metallic cylinder and on the outer surface, right? So we did those. How about we do a hollow but non-conducting dielectric cylinder? Okay. And it's a non-conductor, and it has charge distributed uniformly throughout the inside of the dielectric material. So I don't know what number this is in all the examples that we've done. Anyone remember? 7, 8, 9,
6.
5?
No, we're on 6.
And I did some parts A, B's, and C's.
Can we already do six?
Let's call it 6.
Let me see.
So this will be a hollow. That means there's a hole inside. Dielectric. That means non-conducting. Cylinder. And this will be like infinitely long. I mean, there is no such thing. The result that we are going to obtain, nothing is infinitely long, right? No wire is infinitely long, but the result that we are going to obtain is if you are very close to the wire or inside the wire and very far away from the endpoints. Let's say charge uniform. How about I add the word uniform? Charge per unit volume, rho, inner, radius A, and outer radius B. Calculate E. That doesn't say calculate. Everywhere. So what we have is this. Very long cylinder. It's hollow. So the inner radius is A, and the outer radius is B. So this is the actual material. And we want to know the electric field everywhere in space. So for example here, what's the electric field there? And what's the electric field here? And what's the electric field here? There are 3 places, right, that I'm interested in. So the first one, this one, that's going to be for R less than A, right? So what do I do? It's an infinitely long wire. So what is it that I need to imagine? A cylinder. Is the cylinder infinitely long or of finite length that I imagined? Finite length, because it's got to be a closed cylinder that I have to imagine. And it has to pass through that point. So I'm going to imagine a Gaussian surface like this, which is a cylinder of radius r, and the length is L. So this is my Gaussian surface. I'm just going to call it GS. All right, and then I write down Gauss's law. So, if I imagine the correct Gaussian surface, this integral on the left-hand side of Gauss's law becomes just, an electric field magnitude multiplied by an area. So what's the area that I should multiply that electric field by? Exactly. It's the surface area of it. It's the curved surface area that we discussed the other day. So it's 2 pi r times L. This is the electric field at the Gaussian surface. So that's the electric field right there at the Gaussian surface, right? And then this equals 1 over epsilon naught, which is the electrical permittivity of free space, of vacuum, multiplied by the total charge inside my Gaussian surface. What is the total charge inside this Gaussian surface? 0. There's no charge in there, right? So therefore, right there, the electric field is 0. Are we good? Yes? There's no charge in here, inside my Gaussian surface. So now I'm going to calculate the electric field inside the dielectric material where, where the atoms are. That radius or that distance from the axis is less than b, but it's going to be greater than a. So that's for the electric field over here. I'll just say right there. So what do? I imagine a Gaussian surface, right, passing through that point. So I will imagine a Gaussian surface like this, right? A radius r and length L. And I write down Gauss's law. So this becomes what? E multiplied by what? What is the area of the Gaussian surface, of this cylindrical Gaussian surface that I imagine? Do I care about the two faces and the curved surface, or just the curved surface, not the two faces, or just the two faces and not the curved surface? So which is the one that matters? The curved surface, right? So this is my Gaussian surface. All right, so what is the area of that? Curved surface, a radius r, length L. So what is it? 2 pi r L. The same student is telling me these areas. You know the area of the curved surface of a cylinder, right? Think of a ring, 2 pi r, that's the distance around, times L. So 2 pi r, L. And I like to write down the electrical permittivity of free space first, because sometimes you spend so much time on the Q enclosed that you forget to include the epsilon, to divide by epsilon. So I just write that first and then I do the rest. Okay, so what is the total charge inside the Gaussian surface? So it's going to be the charge over here, right? All the way around. So what is that charge? If the charge per unit volume is rho, so it would be what? Here's the charge per unit volume. Let's say that's rho. So, and that's what was given, right? Uniform charge distribution. So what is the total charge inside my Gaussian surface? Tell me what to write down. Rho times what?
2 pi RL minus,
It's a volume,
oh, sorry.
not an area. So what should I write this? What should I write down?
4, no wait.
Pi r squared L minus pi a squared L. All in
Same student. Yes? What's the volume of this sphere? I'm sorry, not sphere, cylinder. You know, the volume between this cylinder and this cylinder. So if I do pi r squared times L is the volume of all the cylinder, right? But then I gotta subtract out because there's no charge up to radius A. So I have to subtract that volume. So it's the difference between the volume of the cylinder in green and the volume of the cylinder in black because there's no charge over here. The charge is only in the blue shaded area. So it's the volume of that minus the volume of the inner one. So this is the volume, pi r squared, area of the base times the height. So pi r squared L minus pi a squared L. And the next line is just algebra, right? I can cancel this pi with this pi and that pi. I can cancel this L with this L and that L. So I'm going to obtain something like this. Rho r squared minus a squared divided by 2 epsilon naught r. And what about the electric field outside? That would be R greater than B. So what if I want to know the electric field generated by this charge distribution here? So of radius R, where that R is greater than the outer radius B. So then I imagine a Gaussian surface passing through that point with the same axis as the axis of the given cylinder. So this is my Gaussian surface. And so I want E dot dA equals epsilon naught Q enclosed, right? So this is E times, don't say anything. Yeah, let's the other students. Tell me what I should be writing down.
2 pi RL.
2 pi RL, good. And what is the charge enclosed? Well, how much charge is enclosed by this Gaussian surface? Well, to help you out, let me shade that. So it's that and that, right? From radius A to radius B. So what is that charge? What should I write down?
Pi b squared L minus pi a squared L.
Like this?
Yep.
I'm
Okay.
missing something. What am I
Oh, times
missing?
rho.
Times rho, because this is just a volume, not a charge. And if I multiply that by the charge per volume, then I'm going to get a charge. And then again, I can cancel the pi's and the L's. So I get that E equals rho times B squared minus A squared over 2 epsilon naught R. Right? So there we have it. We have the electric field generated by this charge distribution in all three regions. In the hollow area, in the region where there is the dielectric, and outside of that, where R is greater than the outer radius of the dielectric. And look, all of these problems have no more than 3 lines, and the first line is Gauss's law. So it's really boom, boom. But when I write the first exam, and I will include a Gauss's law problem, right? The physics is going to be in this line. I mean, this is given, so you're not gonna get partial credit for that. Right? To go from here to there, well, gee, that's algebra. Right? So this is where you have to slow down and write down very, very carefully, because if you write down something, you're missing the L, or you put R when you were supposed to put R squared, or you put R squared minus B squared when it was, any mistake on this line, that's it for that part of the problem. It's just wrong. Right? The next line is an algebra. So you're not going to get points for Gauss's law because you're given that. To go from here to there is just algebra. I mean, middle school algebra, high school algebra, right? So this is where the physics comes in. So make sure that you write that line correctly. Otherwise, if you make a mistake from here to there, I'll just knock off 1 point. But if this is wrong, if you put like pi r squared, pi RL, and you forget the 2, then that line is wrong. You don't get partial credit for wrong mathematical expressions, right? Or this is where the physics of the problem comes in, right? So this is where you need to be very careful, right? Because after that, it's just algebra. Yes? So when you go over Gauss's law for the various examples that I've done, then you'll be able to see that pattern, what it is that I'm writing down, how it is that I'm doing it, right? And then you'll be able to work more quickly, and then it'll become easier. Okay, so what I would like to do next is the infinitely large sheet. Can I erase this now? And now this is a different geometry. So I will go through the derivation in detail, and then we're just going to remember the result and learn how to apply it, right? Okay, so can I erase this? So I guess this would be, did I write 6 before? So is the 7? So this is the infinitely large sheet with uniform charge per unit area sigma. So lambda is used to denote charge per unit length. Sigma is charge per unit area. Rho is charge per unit volume. And what I am going to consider is a sheet like this with charge here and charge there. And instead of looking at it like this, I'm going to look at it like that. Okay? Because then I can say, what's it that you feel here? What's it that you feel there, right? If I have it like this, then it's in front and behind, but then I wouldn't be able to see behind. So the infinitely large sheet is this. Let's say this is plus sigma. All right, and it's large. I mean, it's large into and out of the board, up and down. There's no way to get from one side to the other side without crossing the sheet. And I want to know what's it that you feel right here. Okay? Now, if this plane is very large, infinitely large, then it doesn't matter how far we are from it because you will never see the edges of it, right? So when we are given an infinitely large sheet, what is the Gaussian surface that we have to imagine? A cylinder, correct? And notice that I wrote cylinder with a capital C as opposed to a lowercase c. Because for the wires of the cylinder, I wrote cylinders with a lowercase c. There was I did that deliberately. Right? Because the cylinder that we imagine is something like this. I mean, if this were a wire, the cylinder that we would have imagined would be something like this. So it's in a different, it's 90 degrees compared to this one, right? Rotated 90. This one, if this were a wire, then we put the wire on the axis of the Gaussian surface that we imagined. Now it's stuck in a different way. So that in the lecture notes, which is a picture from the textbook, I'm imagining a cylinder like this that's like stuck. Okay? So this is my Gaussian surface. All right, when we write down Gauss's law, it's the integral, the circle means over the entire Gaussian surface, all around it, right? Of the electric field at the Gaussian surface, dotted with a vector for the Gaussian surface that's perpendicular to the surface and pointing outwards. And this is related, this dot product, which is a scalar quantity, is related to the total charge inside the Gaussian surface divided by that constant. So, would you like me to first draw the electric field vectors everywhere on the Gaussian surface or the area vectors? You tell me, which one would you like me to do first?
Electric field.
Electric fields? Okay. So what would be the electric field direction at this point? On that face of the Gaussian surface. Which one would the electric field be pointing?
To the right.
To the right, away from the charge, correct. What about on this other face?
To the left.
To the left, all right. What about at this point on the curved surface?
To the left.
What generates the electric field? The charge. And the charge is what? Positive or negative?
Positive.
So it should point
Left.
to the left, away from the charge, right? What about over here? To the right, away from the charge. What about here? Away from the charge. What about here? Away from the charge. Now, what about the electric field vector? I'm sorry, the area vector. What do we need to remember? The area vector is what? Perpendicular to the Gaussian surface and pointing outwards or inwards? Outwards. So if I consider phase, let me give this names. Let me call this phase number 1. Let me call this phase number 2. And then this will be the curved surface of the cylinder. And let me erase this because this was with reference to another discussion. All right, for phase number 1, what is the direction of the area vector? To the left. I'll just call it, should I call it VA? Or I'll just call it A, to the left. What's the direction of the area vector here? Perpendicular to the surface. And the area of that face is the same as the area of the other face. So I'll just call it capital A as well. What about for the curved surface at this point? Which way would the area vector be pointing? Up, right? Perpendicular to the surface and going outwards, right? What about at this point of the curved surface? Up. Perpendicular to the surface and going outwards, right? Choosing this point, which way would it point?
Down.
Exactly, down. And at this point?
Down.
Okay, so, and notice that we are interested in the dot product of the electric field at every point on the surface with the area vector at those locations where I have this electric field. So that means that I'm concerned with the cosine of the angle between those two vectors. So you notice that if I consider face number 2, the angle between the electric field vector and the area vector is 0 degrees. On face number 1, the angle between those two is 0 degrees, but everywhere on the curved surface, the angle between the electric field vector and the area vector is 90 degrees, right? So this integral, which is a sum of E dot dA over the entire Gaussian surface, can be split into a sum of 3 integrals. E dot dA over face number 1 plus E dot dA over face number 2 plus E dot dA over the curved surface. And that equals the total charge inside the Gaussian surface divided by epsilon naught. And over face number 1, the angle between the area vector and the electric field is 0 degrees. So this is 0 degrees, and the cosine of 0 is going to be 1, right? For face number 2, the angle between the electric field vector and the area vector is also 0 degrees. And remember that the cosine of 0 degrees is 1. So those two terms are going to survive. But for the curved surface, the angle between the electric field vector and the area vector is 90 degrees. And remember that the cosine of 90 degrees is 0. So this one is going to be out. It will not contribute. So we get over face number 1, E dA cosine of 0 degrees plus face number 2, E dA plus 0 equals, what is the total charge inside the Gaussian surface? Look at the Gaussian surface, what will be the total charge? The charge will be here, right? What's the area of that? Same A, right? And what is the charge per unit area?
Rho, sigma?
So what is the total charge in here? That's the charge enclosed. That's the only charge inside my Gaussian surface.
Sigma.
That cylindrical Gaussian surface that I imagine. So what's the total charge?
Sigma.
The charge per unit area. So what is it?
Sigma pi r squared.
But instead of pi r squared, I'm calling it capital A, right?
Oh.
So I'm just calling it sigma A. Or sigma times pi times the radius of that square, right? Now, this electric field comes outside. And what is the integral of the A over face number 1? What is the sum of all the area elements over this face? It's just that area. The electric field over that area is going to be constant because it's at the same distance away from the charge. So that will be this, times the cosine of 0, which is 1. And for face number 2, you also have E times the same area, plus 0 equals sigma A over epsilon naught. You get 2EA equals sigma A over epsilon naught. Notice that the A's cancel. It doesn't matter how big of a Gaussian surface I imagine. If it's thin, thick, it doesn't matter. And the magnitude of the electric field is sigma over 2 epsilon naught. If the charge is positive, it points away from the sheet. If the charge is negative, it points towards it. This allows you to figure out the magnitude of that electric field. And notice the result. Does the magnitude of the electric field depend on how far away you are from the sheet? Because it's infinitely large. It doesn't matter if you're 1 meter, 2 meters, 3 meters, 4 meters, the thing is infinitely large. So you get, this is independent of distance, this is uniform. Interesting result. Now, look in your notes, and when we were in chapter 21, we solved this problem of a disk, a radius A, total charge Q, and we found the electric field somewhere on the axis of that disk. And I don't remember though. I think it had 2 terms. Was it? I just don't remember. I mean, I don't memorize those things. But probably something like this. I don't know if there was something like that. Oh, there's no, yeah, something like that. Was it something like that? Or I have to look it up. I don't.
It was that with I hat.
Oh, the I hat is just away from it. And then what happens, we took the limit when this x is very small. Like we're very, very, very close to it. If we're very, very close to it, right, then x is like 0, and then this goes away. And what do you get? I only wrote that because I knew this answer. Otherwise, I wouldn't have done it. And I think we got this result. There was one of the limits that we took. Is that what we got in your notes, if you look in your notes? At some point, we calculated the electric field for any distance x away from the disk, and then I took 2 limits. One of the limits that I took was, what if we are very far away from the disk? And we showed that the electric field was given by kq over x squared. But we also took the other limit, and we get a result. And I said, we're going to do this problem again using Gauss's law when you are very, very close to the disk. So close, if you are that close, this disk looks like it's infinitely big. And we should get this result. And that is what we got. So look in your notes and check. So, we have, probably we had this in terms of K and Q, but then I think I actually did that, took that limit and then showed that it is equal to this result. Yes? So, this is a result that you don't, it's like kq of r squared. Like today's quiz, I asked you, what is the electric field at this point due to these 3 charges, right? So, you don't do Gauss's law for each point charge. You just remember the result is kq of r squared, and then, if the charge is positive, the electric field points away from it. If the charge is negative, the electric field points towards it. So it's the same thing with the infinitely large sheet. If the charge is positive, then the electric field points away from it. If it's negative, it points towards it. But how big is it? Sigma over 2 epsilon naught. So how can we use this? So, are we good? Can I erase some of this? So from now on, I'm not going to do this derivation in detail. We're just going to use that result. If the charge is positive, it's away from the charge. If it's negative, it's towards the charge. That's it. So I'm going to call this number 8. So how did we solve today's quiz? I gave you 3-point charges, at 3 corners of a rectangle, and I asked what is the electric field at the 4th corner, right? And what you did is you found the electric field at that corner due to each charge. And then you added the 3 vectors to get the net electric field. That's called the superposition principle. So I am going to apply the superposition principle again to show you how we can use this result. All right. What if we have, and this is now number 8, I think I said, right? All right, so this would be 2 parallel, oppositely charged sheets with charge per unit area, sigma. Well, I said oppositely charged. So one of them has a charge of plus sigma, and the other one has a charge of minus sigma. And remember that when we had one sheet, what was the electric field magnitude over there? Sigma over 2 epsilon naught, right? Okay, now we have 3 regions of interest. I want to know the electric field here, to the left of both of them, somewhere in between, and somewhere to the right. So the question is calculate E everywhere. Okay? Okay, how about we do it over here? So all I do is like when I was given 2-point charges. You don't use Gauss's law for each charge. You just use the result that was obtained using Gauss's law for each charge, and then you invoke the superposition principle. So what will be the magnitude and direction of the electric field produced over here by this positively charged sheet?
To the left.
And how big? Sigma over 2 epsilon naught. Now, at the same location, what is the direction and magnitude of the electric field generated by the negatively charged plate?
Same thing.
Which one?
To the left. Or wait. Right.
Due to the negatively charged plate.
To the right.
Towards it. Don't forget, that's basic, basic, basic. If it's positive, the electric field is away from it, produced by it, right? If it's negative, it's towards it. That's basic, right? So it's this way. And it's sigma over 2 epsilon naught. That's the magnitude. Because I gave them the same magnitude sigma, except that one is positive, the other one is negative. What will you get when you add these 2 vectors? When you superimpose these 2 vectors? You're going to get? Exactly. What about this point here? At that point, the positively charged plate or sheet generates an electric field of what magnitude pointing which way?
Sigma over 2.
Away from it. This is positive, right? And the magnitude is sigma over 2 epsilon naught. What about here? I mean, there, generated by the negatively charged plate.
Towards it with the same
Towards
magnitude.
it. So what will be the sum of those 2 vectors? Maybe I'll write net. And what about somewhere in between them? Somewhere, anywhere. What is the electric field there, magnitude and direction generated by the positively charged plate? To the right, and how big? Sigma over 2 epsilon naught. What about at the same point, generated by the negatively charged plate? To the right. Same magnitude. And what will be the sum of those 2 vectors? So I get asked this question a lot by students. They say, I see this expression written in two ways. And they say, why is it missing in one of them? Why is it not in the other one? So what do you say to them if somebody asks you a question like that? There's a 2 in one of these expressions and there isn't a 2 in the other expression, in the denominator, right? So what's up? How come there's a 2 in one of them but not 2 in the other one? What do you explain to them? What would you say to them? Like, somebody is taking a class in physics and says, oh, you're taking physics at OCC. And I see this formula written, well, I see these 2 formulas and I'm confused. When do I use the 2 and when do I not use the 2? What do you tell them?
When you're in between the two fields, since they like compound, then you don't use the 2, or you remove the 2 from the denominator. And then when you're
And if there's a 2?
when you're outside of the
But outside this is 0.
oh singular.
If there is a 2, it's one sheet that's generating it. This is the electric field for one sheet. If there's no 2, it's the electric field between 2 sheets that are oppositely charged. So notice, if there's no 2, it's because it's due to 2 sheets. Because each one contributes a half. And a half plus a half is 1, and the 2 disappears. And if there's a 2, well, it's only one sheet. It's confusing, but maybe it is, maybe it isn't. What I do, would I remember the result, for example, if I have a point charge Q here and a negatively point charge over there, and I want to know the electric field halfway between them, right? And I don't memorize those expressions. For me, it's enough to just know the electric field due to one of them. And then I'll just use the superposition principle if I have 2, 3, 4, 5 of them. So same thing over here. The one that I remember is this. Give me some time and I'll show you where this comes from. From the basic one. What if you have 3 sheets? Let's make it a little more complicated. 1, 2, 3. And let's make them different. What sign would you like this one to be, plus or minus? Plus. What about the one in the middle?
Minus.
And the one on the right?
Plus.
Okay. Where would you like me to calculate the electric field? To the left of all of them? In between the plus and the minus, this here? Or here? Or there? Of both of them? Of all of them? Here? Okay. So what is the electric field right there? Well, what I would do is this. I would say the positively charged sheet will generate an electric field here pointing which way? The sigma 1. Which way? To the left? Away from it, right? And what's the magnitude of that? Sigma 1 over 2 epsilon naught. What about the electric field there due to the negatively charged sheet? To the
So, right.
And how big is that going to be?
Sigma.
2 over 2 epsilon naught. Right? And what about the electric field there due to the the third sheet, which is the positively charged with charge per area sigma 3?
Sigma 3 over 2
To the
left.
To the left. I'm just going to move it up here. So that will be sigma 3 over 2 epsilon naught. Okay. You want me to tell you the total electric field? I can do this. I'm going to say this is the y-axis and this is the x-axis. Therefore, what is E1? E1 is to the left, so that will be sigma 1 over 2 epsilon naught in the minus I hat direction. What is E2? Due to the second one. That's the one to the right, correct? So that's sigma 2 over 2 epsilon naught I hat. And what is E3? That's due to this one, right? That's positive, so it's away from it, so that would be sigma 3 over 2 epsilon naught minus I hat. So, the total electric field over there will be the sum of these three vectors. So that would be sigma 1 over 2 epsilon naught, and that's, minus I hat, right? Plus sigma 2 over 2 epsilon naught. I should say I hat, maybe I'll do this. And then plus sigma 3 over 2 epsilon naught minus I hat. And I can factor out I hat. Actually, I can factor out 1 over 2 epsilon naught, the I hat, E net, and I have sigma 2 is positive, right? That's it. And give me numbers and I'll plug it in and I'll give you an answer. Yes? Question? It has to make sense. Yes? I mean, this is just writing these three vectors as vectors. But I'm adding all of them, right, together. In this case, I can factor out the I hat because are we good? So that's this sheets. And I've done quite a few Gauss's law problems. I mean, there's another type of problem that you should know how to do. But before I erase this one here, the electric field is, notice the following. I didn't write down the comment. What can you say if you have oppositely charged sheets, plus sigma and minus sigma? The electric field outside is 0, outside of both of them. The electric field is something between them. Notice that the electric field points, well, from plus to minus. And the magnitude is sigma over epsilon naught. And notice that the electric field in this region always points to the right and always has the same magnitude. It doesn't matter if I ask you here, there, 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 there. As long as I'm, very far away from the edges, it's the same magnitude and the same direction. Therefore, it is uniform. So this is the classic example of an electric field that's generated over some region of space, and that electric field has the same magnitude and the same direction. So therefore, it is said to be uniform. When we study chapter 28, we are going to do magnetic field calculations. And we are going to come up with a problem where over some region of space, the magnetic field is going to point in the same direction and everywhere in space. So it'll be uniform. Right? And that's one comment. Then other comment that I want to make, which is to set up chapter 23, is the following, right? What if we have a region of space where there is an electric field, and it's uniform like this? Oppositely charged sheets. Okay, so it's got some magnitude